So, are we okay with all of these? I mean, I know all I've said is that we assumed them. Are the assumptions valid? That's the question now. Are these assumptions valid for surface waves? Now, remember, I was talking about the trajectory of a flow parcel, and then I was talking about the instantaneous velocity field of flow parcels under a propagating wave. It doesn't sit well with one of these assumptions. So I would say that we're okay with all of these assumptions apart from the first one. This is not true. The flow is not steady. Okay? The flow is very time dependent. The velocity field in a particular position varies cyclically with time in a surface wave. Right? I'll show you. 1 minute it's going this way, then it's going up, then it's going down, then it's going that way. Right? That's a surface wave. This is obviously not true. So how do we get around that? We want to apply Bernoulli's equation to surface waves. Obviously we can't. It's the wrong theory, right? Well, we have to use a trick. Okay, so what we do is we transform the coordinates. So instead of having x as our horizontal coordinate, so we're back to waves now, we're back to x, y plane, we're back to the expressions that we derived for the kinematics of waves. And if we say instead of x being our horizontal coordinate, we use x minus omega t over k. So omega over k is the phase speed, right? So it's x minus the phase speed times t. So instead of using x as our coordinate, we're actually traveling with the crest of the wave as our coordinate now. Our coordinates are relative to a given phase in the wave, right? So that means that instead of having a wave that's propagating through our coordinate system, we have a wave which is nailed in place on our coordinate system. This thing does not move, right? But what happens instead is that the flow is rushing backwards through this coordinate system, because remember, we're traveling with a wave, okay? So we're experiencing different bodies of water as we propagate along in our coordinate system, which means effectively, from our new perspective, the water is flowing the other way very quickly, on average, at the phase speed of the wave, right? So if we do that, then we're okay, right? We have a time-independent flow field, because all the features of the flow field, which are related to the phase of the wave, all those features are now nailed in place. So there you are. We just have to apply this coordinates transformation to our expressions. So we can apply it to the vertical velocity, w dash, which is, we just substitute the x into here, so it's az omega sine kx dash. U dash is, well, it's u minus omega over k. It's u minus the phase speed. So because we're differentiating this with respect to time. So it's dx by dt minus omega over k. Yeah. Then we substitute for u with kx dash here, so there we have u dash. So those are our new expressions for w and u. And so we can now substitute those back into our, well, we can substitute those into our Bernoulli's equation, right? That's the game now. We're going to take this Bernoulli's equation, so we have a u squared here, right? And pressure, force, and gravity. We're going to try and write down that Bernoulli equation in terms of what we know about the kinematics of our wave in its new coordinate system, right? So let's just do that. So remember, Bernoulli's equation is the conservation of energy. So we have some energy here is the pressure. Now, this is the pressure work term, but I've just called it PA. It's the pressure of the atmosphere. What we're going to do is going to apply Bernoulli's equation at the surface, right? So at the surface, the pressure is just PA, the pressure of the atmosphere. V squared over 2. Now, V is the speed of the flow, which is what you get when you resolve U and W, okay? That's what I call V here. So that's just the kinetic energy. And then G dz, G delta Z, that is, delta Z is the displacement of the surface. It goes up and down with the wave. And we have g here, right? So the tricky one, or the complicated one, is this one, the kinetic energy term. So we're just going to work that out. So in our new coordinate system, the amount of energy in the system is not going to be influenced by a linear change in coordinate system, right? So we can just write it down. In our coordinate system, v squared is equal to u dash squared plus w dash squared. And we take those two expressions that we had before, these two, and we just substitute, we just square them, right? So if we square those two things, we're going to get a bunch of terms. So it's going to look quite complicated. We get all these terms, right? So remember, from the first one, u squared, we have two terms. We have these two terms. We have a u squared, which is this squared, right? And we have omega squared over k squared. We have omega squared over k squared. And then we have the two cross terms, so it's 2 times this times this, right? So there we have the u squared term, we have the omega squared over k squared term, and we have the 2 times the product of the two, okay? And then finally, we have a w squared, which is just the square of this, az squared, omega squared, sine squared, kx squared, right? So that's this. But we've substituted the expression for w because, see, these expressions here are the part of the amplitude coefficient that we worked out before, right? So we spent a long time working out the wave amplitude. We're substituting it in here. Now that is hideously complicated, right? So the next thing we want to do is simplify it. So here's an approximation we're going to make, right? We're going to say that z plus h is approximately equal to h. We can say that because we're at the surface. So z is just delta z. It's quite small, right? So we're assuming that the amplitude of the wave at the surface is small compared to the depth of the fluid. Okay? That's a fairly good assumption, unless you've got really big waves right at the shore, which is actually true sometimes. Okay? This is a fairly good approximation. That means our theory is going to break down, though, when you get really big surfing waves in very shallow water. So if we do that, we can simplify it like this. So we've simplified all these z plus h's in these hyperbolic terms, right? And that simplifies it quite a lot. Okay. Now, it's not simple enough. What we're going to do now is assume that wave amplitudes are small compared to the wavelength. Okay? So that means that not only is the amplitude small compared to the depth of the fluid, it's also small compared to the wavelength. Right? And it's a separate assumption that we can apply separately. And so that means that A is much less than 1 over K, which means that Ka is much less than 1, Ka squared is much less than Ka. All right, so let's try and look at all the Kas in this expression. We have effectively A squared here, and we have K squared down here, a K down here. So if we multiply this equation, if we were to multiply this equation through by K squared, we'd have a K squared, A squared here. We'd just have omega squared here. We'd have just a Ka here. So this one for sure we can neglect, okay, compared to these two. So all the terms in blue we can neglect with that assumption. So that leaves us just with this part, all right? So at least that's a little bit simpler. And so if we add that part to the rest of Bernoulli's equation, so I've added in now the pressure term and the gravity force term. So that's the whole energy now. And we can just have a look at that. That is conserved. That is a quantity which is conserved, right? Now, the thing is that if it's conserved, that means it must be conserved across all phases of the wave, right? So it means it must be conserved as my fluid flows through my new coordinate system, it will encounter all the different phases of the wave, right? And it's conserved, which means it must be independent of this x prime here. Okay? Which means that whatever the value of this, which is a constant. This must not vary, okay? But since these are trigonometric functions, the only way for them not to vary is to say that separately this part of the expression must equal 0, okay? Which means that this equals 0. So because these two together must cancel out, this is 0. And I've removed the cosine part of it because it cancels out, so we have this expression. It's getting simpler now, okay? And so we can rewrite this expression, which is just two terms left, the gravity term and this term. We can rewrite that. The A will go, okay? And we can write it in terms of omega squared. Because what we want at the end is a relationship between omega and k. And here we have it, right? So omega squared equals gk times the hyperbolic tangent of kh. And this is it. We've done it. This is the dispersion relation, okay? This is a general dispersion relation for surface waves, surface gravity waves. The assumptions we have made along the way, and let's just remember them, okay? The first assumptions we made were that it was non-divergent and irrotational. That was way back when we were doing kinematics. Then we assumed that basically we could ignore friction. The last few assumptions we made were to do with the wave amplitude, right? We assumed that the wave amplitude was small compared to the depth. We assumed that the wave amplitude was small compared to the wavelength, right? And that has allowed us to get to this relatively simple expression for the dispersion relation. And so this is very well known. This is the dispersion relation for surface waves.